Welcome back to Calculus for Economics. Today is Monday, March 30th, and we're going to talk about a new topic today, an application of exponential and log functions to compound interest. Uh, so, compound interest is really the kind of interest that you experience if you have a savings account, and in more sort of elaborate versions, it's the kind of interest that comes whenever you cycle the earnings you get on an estimate on an investment back into the principal of that investment itself. So to begin, let's talk about a simpler idea, the idea of simple interest. Um, Suppose you open a savings account with $1,000. The account pays 2% interest annually. How much interest do you earn after 1 year? Well, this is a pretty basic computation that most of us probably already know how to make. The interest would just be your principal, which is $1,000, times that 2% you earn per year. So if you leave it in for 1 year, you would earn 1,000 times 0.02, which is $20. And notice we converted the 2% to a decimal. So 2% is 2 out of 100, or 0.02. What if you think about the same problem, but now instead of 1 year, how much interest do you earn after 2 years? Well, then the answer would be you've got $1,000 earning 2% for 2 years. So it would be $40. So the idea there is it's the principal times the interest rate per year times the number of years. So that turns out to be $40 in this case. And in general, after T years, the interest you earned would be the principal times the rate times the time, which would be T. So for simple interest, the general formula is that the interest earned is the principal times the annual interest rate times the time that you've had the principal earning interest in years. And so that's just the principle of simple interest. So the accumulated amount would be your principal plus the interest earned. And so that would be P plus P times R times T. That's just the simple interest you've earned. And then you can factor the P out of that to get this expression here. So that is the idea of simple interest. So what's different about compound interest? Well, the only difference is in compound interest, you recycle the interest you've earned back into the principal. And that means that once you've done that, now you're earning interest not only on the original principal, but on the interest that you cycled back into the account. And that turns out to have a really profound effect on the growth rate of your investment. It turns out that with compound interest, the growth rate is actually exponential. And so that's what we're going to be focusing on in this little section of the course. So the first thing we have to think about in terms of compound interest is the compounding period. That is, how often should you take that interest and add it back into the principal? And actually, it's usually the bank that does this automatically. But there's some common compounding periods that you see over and over. One of them is yearly compounding, where you earn simple interest over a year, and then after that year's up, you put the interest back into the principal and you keep going. And there's semi-annual compounding, which happens twice a year. So the interest is accumulated every 6 months and then cycled back into the account. Quarterly compounding would mean you do it 4 times a year. So the interest accumulates every 4 months, sorry, every 3 months, and then you cycle that back into the account and keep going. And then there's monthly compounding. So that would mean every month you cycle the interest back in. And even daily compounding, where you earn interest over a day, and then at the end of each day, you cycle that interest back into the principal. So associated with this is this idea of the compounding frequency, which we denote by the letter M. So M is just the number of compounding periods per year. For yearly compounding, that would be 1. For semi-annual compounding, it would be 2. For quarterly compounding, we'd have m equal 4. Monthly compounding, m would be 12. And daily compounding, m would be 365. So how does compounding work? Well, the basic idea is that simple interest is paid on the accumulated amount during each compounding period. So that means the time that you're applying the simple interest formula would be 1 over the compounding frequency. So for instance, if the compounding frequency were 12, if you're compounding monthly, then the time that you earn simple interest before you cycle it back into the account would be 1 over 12. And remember, the units are years here, so 1 over 12 years would be 1 month. And then you compute that interest, that simple interest earned during each compounding period, and then you cycle it back into the principal. So let's see how that works in terms of just the calculations. Let's denote by A sub k the accumulated amount after the kth compounding period. And so A sub 1 would be the accumulated amount after the very first compounding period. So that would be your principal plus your interest. Now the interest is given by our simple interest formula. The interest rate times the time that the interest is being computed times the principal. But remember, for compound interest, the t is 1 over the compounding frequency. So t is 1 over m. And so you get p plus r times 1 over m times p. And if you factor out the p from that, you get this expression, p times 1 plus r over m. So that would be the amount accumulated after the first compounding period. After the second compounding period, what do you have? Well, remember now, you started out with the amount you had after the first compounding period. So your principal is now A1. And then on that principal, you're going to earn interest rate R for t equals 1 over m time. So we get this expression here. And if you factor out the A1, you get A1 times 1 plus R over m. But now use the expression we had on the previous slide for A1. A1 itself is P times 1 plus R over m. So I'll make that replacement right here. And what you wind up with is P times 1 plus R over m, the quantity squared. So that's the amount that you've accumulated after 2 compounding periods. And this is valid, no matter what the compounding period is. If it's monthly compounding, this would be the amount after 2 months. If it's daily compounding, this would be the amount after 2 days, and so on. Well, that pattern actually continues. Let's just look at the third period. You have the principal you had at the end of the second period, plus the interest you earn on that principal during the third period. And so we get A2 times 1 plus R over m, the quantity. And then from our previous slide, we know that A2 is P times 1 plus R over m squared. And so making that substitution here, we wind up with P times 1 plus R over m cubed. So you see the pattern here. The amount accumulated after a certain number of periods is the initial principal times 1 plus R over m raised to the number of periods that you've been compounding. And so in general, this would be the idea. After k compounding periods, you have P plus 1 plus R over m, all raised to the k power accumulated in your account. And here k could be either 0, 1, 2, or 3. It's an integer, right? Because k is the number of compounding periods that have elapsed. So that's useful in and of itself, but what we'd really like is, just kind of for convenience sake, is to know, rather than how much money we have at the end of 5 compounding periods, I'd like to know how much money I have at any given time t after I've made the initial investment. So how does that work? Well, let's think about how much has accumulated after t years. If you think about it, the number of years that things have been accumulated, if you multiply that by the number of periods per year, the number of compounding periods per year, that would just be your number of compounding periods, which we already have been denoting by K. But the number of compounding periods per year is M, and of course the number of years is T. So that says that if I take the time T in years and multiply it by the number of compounding periods per year, M, I get the number of compounding periods, K. So for instance, if I'm compounding 12 times a year, monthly compounding, and I've had the investment going for 2 years, I would be at 2 times 12, or 24 compounding periods. Well, if we just plug that back into this formula here, you get the expression for the amount that's accumulated after a certain time t. And so basically all you see is that this used to be the K in the previous slide. K is equal to M times T though, and so I've just made that replacement. So the amount accumulated after T years is P times the quantity 1 plus R over M raised to the M times T. This is what's called the compound interest formula. And notice I'm writing it as a function now because I do want to apply what we know about exponential type functions to this situation. So this is the compound interest formula. Let's take a look at an example. Suppose you take $1,000 and you deposit it in an account that pays 2% interest compounded monthly. What is the accumulated amount after 3 years? So all we're going to be doing here is applying our compound interest formula to this situation. We need to identify the variables that are in play here. So our principal is $1,000. Our interest rate is 2%, which I write as a decimal. Our compounding frequency is 12 times a year. This is because the interest is compounded monthly. And the time that we're interested in is 3 years. So if I take those values then and plug them into the compound interest formula, I get this expression. A of 3 is 1,000 times the quantity 1 plus 0.02 over 12 raised to the 12 times 3. And if you just work that out with your calculator, you get $1,061.78 and some change. Your bank's going to report that, just going to round that number to the nearest cent. So that would be $1,061.78. I think it's interesting to compare this number here, this 1,061 that you accumulate under compound interest, to what you would accumulate just under simple interest. Because under simple interest, if you make 2% on $1,000 per year, then you'd make $20 per year. For 3 years, that'd be $60. And so if it were just simple interest, your accumulated amount would just be $1,060 even. You already see that under compound interest, you're getting a little bit more. And that's because under compound interest, you earn interest on the interest you've already earned. And that's what is the magic of compound interest. This little bit extra, just $1.78 extra, may not seem like a lot here, but over time it accumulates. And that's because of the fact that time is in the exponent of this exponential function. And we'll be seeing examples of that later. So even though that may not seem like a big deal, it actually is if you start looking at letting the investment ride for many years. You'll see that difference between compound interest and simple interest gets larger and larger. There's a related concept here called the effective annual interest rate. The effective annual interest rate is the simple interest rate that would yield the same accumulated amount after 1 year of compounding at the given rate of R. So the effective annual rate is sometimes, I think, like on your credit card statement, you may find something called the annual yield or the effective rate. They use different names for it. But it's just translating that compound interest rate into the equivalent simple interest rate you would need to get the same performance on your investment. So, how does that work? Well, let's just set it up. Here's the amount you would accumulate under simple interest at a rate of R effective. And this is over a time period of 1 year. So my T is 1 here, and I'm just applying the accumulated amount under simple interest here. And this is the accumulated amount under compound interest at rate R, again for time T equal 1 year. And so, by definition, if R is the effective rate, these two things should be equal. So we basically just solve this equation for R effective to find the effective rate. We can cancel the P's and we get this equation, and then just subtract 1 from both sides, and you get the effective rate is 1 plus the actual rate. Sometimes in this situation, R is called the nominal rate, divided by M, raised to the nth power, and then minus 1. So that's how you compute the effective rate given a compound interest rate of R. So a quick example there, an account pays 2% interest compounded monthly. What is the effective rate? So the compound rate is 2%, and the number of compounding periods is 12. The compounding frequency is 12, again because of monthly compounding. So I'm just going to plug that into my formula for the effective rate. I get this expression here, and it winds up being 0.020184, and there's some more decimal places after that. But convert that back to a percentage, and I'm rounding to 3 places here, you get 2.018. So the effective rate for 2% interest compounded monthly is actually 2.018%. That gives kind of a basis for comparisons of different schemes of interest. So that is our initial look at compound interest. We'll have more to say about this going forward, but this should help you with homework 31, which is due Tuesday night at 11 p.m. And let me know if you have questions. Stay safe, stay well, and I'll be back in touch soon. Y'all take care.